Welcome to EDU World Space.
This problem, a bit of a involved problem. So what we have here is a 5 meter long wire. So this is a wire, and it weighs 0.732 kilograms, and it's attached to these two rods of equal length L, attached to these pivots, and these rods here, they weigh a certain force, and that force is 235 newtons. So we're combining some mechanics and some wave action here. And so wind is blowing on this apparatus, and it's producing standing waves in the wire, which are vibrating at the fifth overtone, which means n equals 6. We're using the sixth harmonic. So there's a lot of information. We're also given that these rods are fixed to pivots on the ground, and they make a 57-degree angle with the ground. And what we're tasked with is finding the wavelength and the frequency of the sound that the wire produces. So we want to know lambda, and we want to know f. So the important thing to note is that when a wire vibrates and makes a sound, then the frequency of the sound that it produces is going to be the same as the frequency of the wire. So we're going to need that piece of information. So the way we're going to do this is we're going to use torques to figure out some forces here, because we're going to start off with a relation V is equal to lambda F, and just work towards finding lambda and work towards finding F. So first, lambda here is going to be equal to 2L over N, which is we'll save the calculations for later. Actually, yeah, let's go for it. Sometimes it's hard to know what you want to save for later and what you just want to do right now. So 1.67 meters. Frequency, however, is a little bit more involved. So in order to find the frequency, what we're going to do is we're going to note that V is equal to the square root of F over mu, where mu is the mass per unit length, M over L. And we know M and we know L. But the thing is here that we don't know F. And F is going to be the tension in the wire. So we're going to proceed by calculating F. And the way that we're going to do that is, you might remember from mechanics, we're going to draw a free body diagram. So that free body diagram is going to look like this. If we draw the free body diagram for the rod, we're going to have a force down at the middle of 235 newtons. Then the force of the wire pulling it this way, call it F. Actually, since we're not going to be dealing with frequency here, we can be safe, and we could call it F, we could call it T. Anyway, we're going to call it F, and then what we're going to do is we're going to note that this is half the wire, or half the rod here on either side, and we can do consider all the torques about this point, and note that since it's an equilibrium, that the sum of all torques about the pivot point has to be equal to 0. So yeah, if we proceed, then the sum of all torques is going to be W, which I'm going to be calling the weight, times L over 2 times cosine of 57 degrees minus the force times L times sine of 57 degrees, which is equal to 0. And that tells us that F then has to be equal to W over 2 times tan of 57 degrees, which is 235 over twice tan 57 degrees, which ultimately is 76.3 newtons. So now we know mu and we know F, so we can calculate V here. So since V is equal to the square root of F over mu, that is square root of 76.3 newtons divided by 0.732 kilograms, and then again divide that by 5 meters. And that gives us a velocity of 22.9 meters per second. So n equals 6 for the fifth overtone, and we've calculated the wavelength. Now we can go ahead and calculate the frequency. Let's just box this up here in green since it is one of our final answers. Our frequency then is going to be V over lambda, which is 22.9 meters per second divided by 1.67 meters. And that is equal to 13.7 hertz. Yes, and so the sound waves, however, so that's going to be, I'm sorry, I misspoke over here. This is the wavelength of the waves on the wire, but that will generally not be the wavelength of the waves on the sound. On the wire, in the air. Sorry. So this lambda here is going to be the wavelength of the waves on the wire. And while the wire waves and the sound waves share the same frequency, they do not share the same wavelength. So to calculate the wavelength of the sound waves, we're going to have to use V air over lambda, which is, V air over F, which is 344 meters per second divided by 13.7 hertz, which is equal to 25 meters. And that's our final answer for lambda in the air. So to recap, we were tasked with finding the wavelength in the air and the frequency in the air. We were able to find the frequency by using our V is equal to F over mu equation and solving for the force by considering a free body diagram in equilibrium and calculating the torques. We found the wavelength on the wire and used that to also calculate the frequency in the wire. We note that the frequency on the wire is the same as the frequency of the sound waves in the air. And then from that, we're able to calculate the wavelength in the air by using V is equal to lambda F, and then plugging in the speed of sound here, 344 meters per second. So that's involved. I encourage you to look at this as long as it takes to get it. But that's the end of this problem.